First off, before I start today's one, I forgot to do something in the last presentation. I think it's one of our presentations for the exploitation of the properties of the Christopher Civil. I've said once that I'll be calling the name of the books that are particularly helpful. And it's just fair that I mention the book by Joseph Weber, Gravitational Waves. Joseph, I'm writing in G, not Joseph. So Joseph Weber, or Joe Weber by those who know him very well, Gravitational Waves. So one can look into his book, particularly from this chapter 6 upwards, but the whole book is good. Might as well read the whole book. Okay, so now we are going into another property here, or application as one may see it. This stress energy tensor, the stress tensor for a perfect fluid model of the universe. This is very popular stress energy or stress tensor in cosmology and GR. We intend to solve a problem involving this tensor. U mu is the local velocity of the fluid element, P is the pressure, and rho the energy density in a local inertial frame moving with the element. Of course, from the Einstein field equation, it is required that this contraction nu of this the covariant derivative of this stress tensor should give you 0. Now we want to show that using this stress tensor and this condition that we obtain the following hydrodynamic equation. Well, in many ways it might look obvious, but not really that obvious. So very quickly, we have such a tensor as T mu nu to be equal to, as written all over here. So in order to avoid being redundant, let me simply say this is the covariant derivative with respect to that. So I'm taking the entire P G mu nu plus P plus here rho U mu U nu, the entire expression covariantly differentiated with respect to x nu. Of course, I'm going to start first of all by applying the Leibniz rule. So this is going to be P nu G mu nu plus here P G mu nu covariant derivative with respect to that, plus again I treat this as a single object, P plus rho, that gives me nu, U mu, and then U nu. The next plus, again by the usual Leibniz rule, I treat this as a constant, P plus rho, but then U mu, I differentiate that, still keeping the last factor there a constant, and of course plus. So I'm going to have here this same last term, P plus rho, U mu, U nu, and that, and the whole thing should be equal to 0. Very quickly, we make some very interesting identifications. We know that the covariant derivative of the metric tensor is always 0, no matter what kind of metric tensor you're talking about. In general, that is 0. And we have taken note that this is a pressure and this is some energy density. So these two functions are scalars. So their covariant derivative will be the same as just the ordinary derivatives. So I will be changing in this case the semicolons to simply commas. So this will be comma nu. This will be G mu nu, of course this term is gone, plus I'll have here P plus rho, but then this will be comma nu, right? And then followed by U mu, U nu. That is what I get for that. The last two terms, I'm going to be very quick in my expressing them. So I'll say this is simply supposed to be P plus rho. The covariant derivative of what I have here, that's U mu, this is a vector, a contravariant vector, the U mu, the X nu, and to be plus, gamma, of course what I'm contracting is mu, so mu comes over here, and I'm going to use alpha as my contracting index. Alpha, I'm differentiating with respect to nu, and then U here, alpha, and that is what I get for this term. Okay, let me just continue to make this easier for me. Plus, here I have P plus rho, and what I've got is U mu, and then here in the bracket again, I'm going to write out this, and this should give me the U nu, the X nu also, because of course that's what I've got. Then plus, I'm contracting nu, I'm using alpha to do that, and I'm differentiating with respect to nu, and this is what I get. And the whole thing again, of course, like we have said over and over again, should be equal to 0. The whole expression should be equal to 0. Of course. Again, so moving forward, we have been able to make some identifications here. Very interesting. We could see, of course, that, okay, so we're going to leave this first time untouched for now. But it will be very interesting to make some collection of like terms. So let's just say, first of all, this is supposed to be comma nu, G, G, mu, nu, and I have here with us plus P plus rho here, comma nu, this will be comma nu, and we have here u mu, u nu. That's what we get for that. So collecting like terms in the sense here, we are going to take this first one here in the bracket. We are going to multiply this with this. Okay, I think I might have missed a term here, and I think I should make that up immediately, because here we evaluated this in writing this out. So we missed a u nu here. So I'm going to multiply those two. In other words, I have here with me plus some p plus rho here, and I have here du nu, the x nu, multiplied by u nu. Okay, I'm going to leave the second term just for a moment. I'm going to say plus here. Yeah, so I'll just go on plus p plus rho, u mu, the u nu, the x nu. Then plus the second term of this will be this times that times that. And so this is going to be plus p plus rho, gamma mu alpha nu. I have here u alpha and u nu. Then finally plus p here plus rho, which is this u mu. I'm multiplying it with this. Okay, so I think I would like to make that to be in order, just like it's the same thing actually, but just for the sake of some. So this, I'm multiplying this with this. So I'm saying that this should come in this order, nu, and this is going to be, for instance, u mu, and the last thing there is u alpha, and the whole thing should be equal to 0. Okay, now looking at this whole thing as we've written them here, what is next? Well, we can try to make some identifications here. These two terms here, for instance, have something in common. We can try to separate that out. So this is the same thing as p comma nu, g mu nu, plus here p plus rho, comma nu, u mu, u nu. And then I have here plus some p plus rho, then I put a block bracket here. I have here the u mu, the x nu, u nu, plus. I have here u mu, the u nu, the x nu. That is what I have. And of course, as usual, I'm going to have here with me plus p plus rho here, gamma mu, alpha nu, u alpha, u nu, and then plus finally p plus rho here, gamma nu, alpha nu, u mu, u alpha equal to 0. Yeah, so this is what I get for this case. Now at this point in time, what I'm looking at is to kind of condense this. Of course, it's obvious, we can see from here that this looks like some kind of d dx nu of a product of u mu, u nu. Yeah, that's what we have there in the bracket, looks just like that. That's what it should be. And also, so I'm going to be so I have here p comma nu, g mu nu, and I have here with me plus p plus rho, comma nu, u mu nu, and then plus here some p plus rho. Then I'm going to have in a bracket u mu, u nu, the whole of that comma nu. That's what I mean by this, d dx nu by a comma with nu. Okay, so I'm going to bring this last time here. So I have an intention to sort of try to condense this with this. Why do I think I can do that? Because I have nu here. So one of the indices of the affine connector is repeated. And if this is nu, you can see from what we already know, or what we always know about that affine connector, gamma nu, alpha nu. This will be 1 over the square root of minus g, d dx alpha, square root of minus g. Yeah, it's always the x of whatever is standing alone. That which is constructed is not important. But supposing I had something like this, alpha nu alpha, then this would be 1 over the square root of minus g, d dx, but nu, this time around, and not alpha, minus g. So that is what I will have. So I'm going to have d dx nu. So because all the derivatives on the terms here, the various terms here that I'm dealing with, are derivatives with respect to x nu. That is why on this term, I would like to make an interchange between alpha and nu. Yes, not just because I want, but because I can. Yes, alpha is repeated. You can see nu is repeated just on the affine connector, but there's another alpha here. So I'll have to remember to be careful about this, that if I'm making this interchange, the alpha here also has to change to a nu. So moving on, we have written these first two terms and this already here. So I would like to write this next and then write this last. So in other words, I'm going to have plus, but p plus here rho, and what I'm going to have will be instead gamma alpha, nu alpha, and mu will be left all alone, but u instead of alpha there will become nu, and this will be plus, this which I should have written first, now writing last, plus rho, and you can see gamma mu, alpha nu, u alpha, u nu, and the whole of this should be equal to 0. Okay, so moving forward, now we can see something here. No, sorry, I think there was an oversight here, so maybe I should try to sandwich what it should be. I think what I meant to write here was u and u nu. Yeah, that's what it should be. That's what it has been all this while actually. So you can see that these two terms here could sort of be combined. Yeah, because it's just like a Leibniz rule. I kept this, I differentiated with respect to x mu, kept this product a constant. If you like, you can put a bracket again between them. And then plus, I keep this first term a constant, and then differentiate, that's what I did on the second term here, or that's what it appears to be on the second time here. And then you differentiate the second. So you can see that these two can be combined. In other words, what we've got is still this, and this should be equal to here, p comma nu g mu nu plus. Of course, we've written that now plus here. I'm going to have here some p plus rho, and that will be multiplied by u nu, right? That will be multiplied by that. And now I have here to be comma nu. That is what I get. So by Leibniz rule, I've just combined these two terms. And then finally, not necessarily finally, so I'm going to say plus here. So you can see that these factors again could be combined together. So let me just, for the sake of argument, put again another block bracket here. So I have here to be u nu. This is what I get, this combined. Except of course for this last term, which is gamma alpha nu alpha, which is the same thing as 1 all over the square root of minus g, d dx nu, and then times the square root of here minus g. This is what it is. And then of course plus the last term there, which is plus, the last term there is there p plus rho, and then here I'm multiplying it by gamma. I think what I've got here is mu alpha nu. So this is mu alpha nu, and then I have here with me u alpha u nu. The whole thing again is supposed to be equal to 0. Of course, this is our usual friend in every manipulation we have performed so far. Now you can see we can combine these two terms. Just to make that apparent, I'm going to dispense with this comma for now, so that instead I'll say this is d dx nu. Now you can take a look at the two terms. You can see as usual that this whole thing, as usual, we combine them, if you remember, as 1 all over some square root of minus g d dx nu, and then I open a bracket. Or let me use a code, well, that's just a bracket, and it should be p plus rho u mu u nu times the square root of minus g. Of course, it could be before or after, or whatever, it just doesn't matter. But you can see that if I were to expand this, these two terms is what I'll get. So for instance, if I decide to treat this as a constant and differentiate this with respect to x nu, of course this is what I'll get. Because then the square root of minus g, which we are treating as a constant, cancels this. Plus, this time around, we differentiate this, but then keeping this a constant. So you can see I have this to be all over that, then differentiating that with respect to x nu. So these two terms have been combined as that. And finally, you can see, if I become explicit with these two, it therefore means that I have, of course, t mu nu, that to be equal to the p dx nu g mu nu. After that, I have next with me plus 1 all over the square root of minus g d dx dx nu, and then I have there multiplying square root of minus g. I have here p plus rho multiplied by u nu. And of course, this is what it should be. Yes, we're trying to make some connection and making sure that this is all true. Yeah, multiplied by that, so I just simply brought this in front here. And plus, my brackets are running out, plus p plus here rho gamma of mu alpha nu u alpha u nu, and this is all equal to 0. And I believe this is all we have been looking for. Gamma mu alpha nu, gamma mu alpha nu, p plus nu, u alpha u nu. So we're in shape. In other words, this was what we wanted to show, that the Einstein equation which led to this constraint, together with this stress tensor, leads to this hydrodynamic equation. Again, this is all thanks to the book by Pramnath, and I hope again that with time, of course, in our next episode, we see more applications.